Hello everyone, let's solve question 1 on the 2023 AP Chemistry exam together today. And question 1 is talking about manganese, the atom. It is a multivalent actually, so it has lots of oxidation states, but we're asked to write the complete electron configuration for just a regular manganese atom in its normal ground state. Okay, so it's regular electron configuration, so not any electron promotion or anything like that. So to do this, I do need a periodic table. I know AP will give you one, but just so I don't have to scroll all the way back to page 1, I just imported one here. Now, there's different ways you can do electron configuration. I like to do it this way using my quantum blocks. So maybe you remember from your classes that the first two groups, these elements are your S block. Also, that includes helium. That's also S. Boron to neon and everything under it, this is your P block. And then your transition metals in the middle is your D block. So I see manganese here. So what I know is manganese will end with, it's the 1, 2, 3, 4, it's the fifth one over. So I know manganese will end with the D5. And then although we don't need it for this question, the bottom lanthanides and actinides, we call this your F block. So to do this method, what I'm going to do is I'm just going to count from the top, from hydrogen, until I get to manganese. So for example, hydrogen's 1s1. So let's go to helium. Helium's 1s2. So I'm not even close. I have to keep going. So keep going in order. Lithium and beryllium. So this is 2s2. Let's go across from boron all the way to neon. Neon is a 2p6. We're not there at manganese yet, so go down to the next line. Sodium and magnesium. Magnesium is 3s2. Keep going. Let's go across. Aluminum to argon. Argon is going to be 3p6, so aluminum is like 3p1. Silicon 3p2, phosphorus 3p3, and so on and so on. Okay, we're getting close. The next one, potassium and calcium. Potassium 4s1, calcium 4s2. And then the D5, I know manganese is D5. This is actually 3D5 because in quantum, there's no such thing as 1D or 2D. The D block starts at 3, level 3. Okay, so this will be a 3D5. So my final answer here, the complete electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And notice here that the number 4 comes before 3, and that has to do with electron filling. So we do have to put it in this order because this electron filling pattern is based on energy. It's called the Aufbau energy filling principle. And that basically explains that electrons like to fill with lowest energy levels first before getting into higher energy levels. And the 3D, it's more, because it can hold 10 electrons, it does have inherently more energy, even though it's a little bit farther away from the nucleus than 4s. So that will help us with the next part, because it says that when manganese forms a cation, electrons are going to be lost, and we're asked here which ones will be lost first. Identify both the number and letter associated with the subshell. So looking at this electron configuration, like these are all very stable because they're all kind of maximized. Even the 3d5 is somewhat stable because it's, remember, like 3d is like this, right? So each electron orbital has one electron in it, so it's somewhat okay. It's not perfect. Okay, you can go up to 3d10. So it's this 4s2 that's the farthest away. That's my valence shell. That's actually going to be lost first. This represents my valence shell and valence electrons. Okay, it's the farthest away from the nucleus, so it has the least nuclear attraction. So those will be the first ones lost in manganese. Moving on, a student is performing an experiment to produce a manganese salt. So that's this, with an unknown composition, X and Y for the formula. And we want to determine the empirical formula. So to get this product, what the student did was they reacted solid manganese metal with aqueous HCl. So if you want to envision kind of this little experimental setup, you have a little beaker, you're going to put in a solid chunk of magnesium, you're going to put HCl on top of that. We don't know how much yet, so we're going to mix these reactants together. And when you do that, you will get hydrogen gas as a byproduct, and then you'll get some sort of manganese chloride salt, but we don't know what the subscripts are. Okay, so with that information, what are we being asked to do? We have a data table of lab data, And the first thing we have to do is calculate the mass of chlorine that you got in your product. Remember, this is your manganese salt. That's your product, this manganese chloride. Okay, well, when I have an empty beaker, okay, sure, the empty beaker has a certain mass. That's great. Now, when I put the manganese solid in, the mass rose. So if I wanted to know the mass of just the manganese, I would take the difference between these two numbers. And then I'm going to add some HCl on top of that. And then that's what allows me to create this product. So now that I have a product that actually has chlorine in it, so I have to take the difference between these two numbers to determine the mass of chlorine that I have. So the mass of chlorine is going to equal 62.673 grams minus 61.262 grams. That will give me a chlorine mass of 1.411 grams of chlorine. Now that I know the grams of chlorine, I'm being asked to convert this into mole. So that's okay. There's many ways you can do this. I will convert it using, I like to use the mole formula, which is N equals M over molar mass, mass over molar mass. So the mass of the chlorine is going to be the moles of the chlorine is going to be 1.411 grams divided by the molar mass, 35.45 grams per mole. The grams will cancel out, and the mole will reciprocal to the top, and that will give me a mole value of 0.03980. Moving on, the student determines that 0.0199 moles of manganese was used in the experiment. Use your data to determine the empirical formula of manganese chloride. So how you do an empirical formula question is you divide everything by the lowest moles you have to look at the ratio of the two elements or the two atoms you have in this compound. So for example, manganese, we have a mole value of 0.0199 mole. Chlorine, we calculated above, we have a mole value of 0.03980 mole. So what I'm going to do is divide both of them by the one that is the lowest moles, that's the manganese. So that will give me like a ratio of 1 for the manganese. And based on this calculation, what I can, if I just clean it up over here, so manganese, for every one manganese atom, obviously you don't have to write down the one, I'm just doing this to illustrate my point. I will have two chlorine atoms or ions. So therefore, my empirical formula for this is I have a ratio of 1 manganese to 2 chlorine. So the empirical formula is manganese chloride MnCl2. Okay, now let's do one more before we move on to the next part of question 1. I'll start a new part, like a new video part for part 2. The student repeats the experiment using the same amounts of manganese and HCl, and notices that some of the manganese chloride salt splatters out of the beaker as it's heated to dryness. Okay, so again, visualize this, okay? So here's my beaker. I'm mixing my two things. I've got a solid and then HCl, and then I'm going to produce this salt. But what's going to happen is, okay, so let's pretend, okay, actually, let me redraw this. Let's say the salt looks like this, okay? Or whatever you want to do, and then plus it produced some gas. So this is saying some of the salt splattered out. Some of these dots splattered out of the beaker. So if that happens, that's kind of like a lab error, human lab error, or maybe experimental, probably a human lab error. Will the number of moles of chlorine calculated for this trial be greater than, less than, or equal to what you calculated in part C? So that's this value up here. I justify. Well, I think this one's not too bad, because if you're losing products, then the moles, it's not going to be the same thing here, right? You're going to have less of a mass and therefore less of moles. So what we're going to say here is that our answer is we will have less than, and the reason is because the final mass of chlorine, or of even the salt of MnCl will be lower. And then when you convert mass to moles, that's going to decrease the mole value also of that'll decrease the mole value also of the chlorine, right? So if the final mass will be lower, this will cause moles to be lower also. You can word this a little better than I am. Again, always look at the answer key to see their wording, but I hope that gives you the idea. All right, we'll pause it here and we'll go on to one more part to finish up question 1.